All right, let's move on to the next one. Now, this is my favorite, personal favorite, and also it's just a beautiful bridge. I think if you've seen it, it's just amazing how it just spans quietly across a valley, and they say valley of nowhere because it's middle of nowhere. It's just a side road going somewhere, and the bridge has been made. And Salginatobel Bridge in Switzerland is a three-hinged concrete arch. It's just absolutely beautiful aesthetically, and the story behind is equally interesting. So this is designed by the designer called Maillart, and he has designed many bridges, and this is one of his famous ones. There are many other, in fact, that he has done, and he basically replaced the old masonry bridges which were based on mass and created a geometry that will just be enough. Rather than mass, he created a geometry and the materials together and introduced concrete as a material for bridges. Most bridges before that were made in either masonry or in steel, like we have seen the bridges, cable-stayed bridges and or masonry arch bridges were common. But concrete of this kind was not common. So he brought in these two things, and just look at the form of the bridge. Now, this is a very thick, thin bridge, only 20 centimeter thick. The deck is so thin, and it spans 90 meters across. So the beauty of this bridge is in fact many ways. First of all, as you can see aesthetically, it's just a beautiful form, and it combines the deck and the arch into one integral unit. Previously, at that time, even now people construct the arch, they build the columns and build the deck. So deck, columns, transferring the load to the arch, and arch, they are normally three separate systems. In this case, they were all together as conceived as one integral unit, and also they introduced the box girder design at that time. So with so many things that happened. So as you can see, this is a three-hinged arch, and the reason three-hinged arch is used because of the temperature variation. As you know, in Switzerland, it can get very cold and hot also sometimes. So they needed a bridge that could kind of breathe, it can go up and down when it expands. So because the abutments are fixed, so the central arch makes it possible for the bridge to move up and down and to expand without causing any cracks. And it can rotate about the hinges at the base. So that was the idea. The problem with these bridges, the three-hinge arch bridges, often is unsymmetrical loading produces unsymmetrical bending or forces, because if you can balance it, fine for a uniformly distributed load, but it's hard to balance for a point load on one side or half the bridge loaded. That's why Robert Maillart, he did a lot of calculations, but most of his calculation was just graphical drawings of the force flow. He did not believe in complex mathematics. He believed in simple logic and graphical demonstration of force flow. So he drew all the influence lines, he drew all the thrust lines of different location of the loading, and finally he chose the arch that will capture all of the thrust lines from every location of the loading on the bridge. That's why you see the arch thickens in the middle and then becomes smaller in the center, because it's trying to capture all of the possible thrust lines. Because if you have only gravity, you have one thrust line, which is fine. But if you have moving loads and you have loads that can be, half the bridge, then the thrust line will change. So he captured all of the thrust lines neatly into the arch, and then he made it integral with the deck. So it's just in every way, this was a beautiful concept and very well done. And it was considered the most beautiful bridge of the 20th century by several authorities, including the one of the committee who sort of started this bridge in the beginning. So this is still considered to be a masterpiece, and you can see here the reinforcement drawing of that bridge, the vertical walls, the arches vertical. It's a hollow box inside, so it's just very thin walls, and it was so economical compared to anything else. Very low mass, very low cost, and very elegant. And that's why it became so prominent. And many people consider this to be a work of art, purely by an engineer. So you can see once again the beauty of this bridge. So International Historic Civil Engineering Landmark in 1991, and many other awards have been given to this bridge. So let's look at the construction, simulation. It's not actual construction, simulation. And only a few people built the scaffolding required for this one. So you can see the scaffolding being built, wooden scaffolding being built. They claimed only 6 people did that, and they just constructed this scaffolding, and on that then the arch were cast, and then after that the deck was cast, and then the bridge was completed. And then of course the formwork was removed. And look at the beauty of this bridge from every angle. It's just absolutely amazing how it just blends into the environment. So this is where they call structural art. It's a structural engineering project, but at the same time, it's a piece of art or form that is matching with the true to the structural behavior. And here is the designer, Maillart. Actually, his name is quite difficult to pronounce in French, so I will just stick to the English pronunciation of that. And he actually, after that, he designed some other bridges also, who became very famous later on. But his main contribution is this particular bridge. And he won so many awards for his bridge. And he always believed in simple calculations to do the designs rather than complex math. This is actually ETH Zurich, where he studied. Both him and also Maurice Coquelin, who designed the Eiffel Tower, both of them, they studied in ETH Zurich. Not at the same time, but this is, some people say this is the most prominent school of engineering and architecture in the world, especially at that time, because so many people graduated from there. And incidentally, also Einstein studied there and taught there for several years. In fact, if you see the timeline, then Robert was there in '94. Einstein just came 2 years after that. So they must have met each other around that time. So it's a very famous college, university now for engineers and architects, and graduates have done great work.